Hello everyone, and thank you for joining me from around the world. My name is Alec Cusick. I'm a technical services engineer with foam glass at Owens Corning. Excited to be here today as part of the Cryotech 2020 International Online LNG Conference. Looking forward today to talking with you about two foam glass systems specifically designed for cryogenic liquid spill protection and LNG pool fire suppression. Before we get started, I'd just like to take a moment to set the agenda for what we'll be talking about here today. I'm going to start off by talking a little bit about Owens Corning as a company for those that may not be familiar. We'll then move into some priorities that you'd want to consider during a cryogenic liquid spill. We'll then talk about our first system, which is around cryogenic liquid spill protection, followed by our second system we're going to talk about, which is around LNG pool fire suppression. And then at the end, we'll wrap things up by talking about some technical services we offer as a company to help you with your insulation needs. Starting off with some about Owens Corning. Owens Corning is a global industrial and building materials leader with 3 integrated businesses dedicated to the manufacture and advancement of insulation, roofing, and fiberglass composite materials. We have over 18,000 employees across 33 countries around the globe, and we're very proud to have been a member of the Fortune 500 company list for 66 consecutive years. Our insulation business specifically is built around leveraging our global platform to deliver quality products and innovative solutions that are safe, durable, efficient, and high-performing over a wide range of service temperatures. Our product portfolio includes open and closed cell insulation solutions, including foam glass, cellular glass insulation, which we'll be talking about here today, fiberglass, Paroc and thermofiber mineral wool, and foamular extruded polystyrene. Moving on from here, let's move on to the main topic that we came to discuss today, and that is, of course, cryogenic liquid spills. Now, when you think about cryogenic liquid spills, there may be some priorities that come to mind that you think warrant significant attention. I have 3 here outlined that I believe warrant enough consideration to actually warrant discussion during your insulation system selection. These are thermal shock protection of support steel and concrete, reduction of vaporization of liquid hydrocarbons that are present, and the reduction of radiant heat during any fires that are taking place. We'll now discuss each of these 3 priorities a little bit more in depth and have a discussion on each one of them. We're going to start off with our first priority that we mentioned on the previous slide, and that is around thermal shock protection of concrete and steel within your actual containment pit. It should be noted that both concrete and steel can experience structural changes that result in a reduction of load-bearing capacity when suddenly exposed to temperatures of cryogenic liquids, let's say around negative 160 degrees Celsius. When rapidly exposed to subfreezing temperatures, concrete may undergo multiple processes that can cause microfractures to occur. This can include contraction of the solid network, as well as expansion of water freezing within the concrete structure. Carbon steel, on the other hand, may begin to become brittle and fracture at temperatures of around negative 29 degrees Celsius. Certain grades of low-temperature stainless steel may be tolerant to as low temperatures as negative 48 degrees Celsius. However, it should be noted that these special grades of stainless steel can prove to be quite expensive. It can really expand the cost of a construction of a containment pit should they be required on site. The second priority I'd like to talk with you about here today involves the reduction of vaporization of any liquid hydrocarbons that may be present within a containment pit. In the event of a spill, cryogenic liquid is exposed to various heat sources very rapidly. This could be from the warm air above it, solar radiation from the sun should it be overhead, as well as the warm concrete and ground that it's in direct contact with. LNG specifically gives off invisible, flammable vapors when it's allowed to boil off in this manner. These invisible vapors are flammable within certain concentrations, generally within 5 to 15%. This poses a problem because these vapors may not reach this flammable range until they're allowed to travel a certain distance away from the pit, where they may inevitably run into a source of ignition. This creates a fire hazard not only in the nearby vicinity of the pit, but anywhere downstream from wind sources where those fumes could then travel and cause an ignition to take place. I'd like to point out that in the photo you see here on the right, in the event of a spill, a cloud of condensed water vapor does become visible. Now, this cloud itself is not inherently the problem, as it is just water vapor. However, it is very indicative of the presence of these flammable fumes being given off. The final priority I'd like to talk with you about here today involves the reduction of radiant heat for any fires that are taking place within your pit. Fires, should they be allowed to occur, quickly become the most significant source of heat gain back into the cryogenic liquid. This increases the rate of vaporization, adding more fuel to the fire, making the fire grow larger, adding more heat back into the liquid, and you can quickly see how this leads to a self-propagating reaction. The National Fire Protection Association 59A is the standard for the production, storage, and handling of LNG, and can contribute to the conditional withholding and final denial of regulatory approval for LNG projects. Requirements for exclusion zones can impact overall site layout and design, with direct impact on land acquisition and construction costs for facility owners. Mandated exclusion zones for LNG facilities include parameters for both vapor dispersion and thermal radiation. However, NFPA 59A does allow for the use of passive fire mitigation techniques in the calculation of radiant heat distances, subject to the approval of the agency having jurisdiction. So now that we've talked a little bit about the priorities we're focusing on here today, let's move on to our first system that I'd like to introduce you guys to, and that is our foam glass cryospill protection system. Before we get started, I'd like to just do a quick overview of foam glass, cellular glass insulation as a whole for those that may not be familiar. For those that don't know, foam glass 1 insulation is a lightweight, rigid material composed of millions of completely sealed glass cells. It is impermeable and non-absorbent, corrosion and chemically resistant, inorganic, non-combustible, 100% closed cell, and offers superior compressive strength when compared to comparable insulation materials on the market. It also boasts a wide surface temperature range from -248 all the way to +482 degrees centigrade. Because of these unique properties, foam glass is actually widely used today in many LNG applications around the globe. It's used on pipe and equipment insulation systems, underneath tank bases, and even for fire protection systems on piping and equipment. So what is our Cryospill protection system? Well, it's a system that leverages these unique properties of our foam glass insulation to provide a permanent, weather-resistant insulating barrier on the inside of your containment pit. It provides thermal shock protection of support steel and concrete of the pit walls and floor, and reduces the vaporization of liquid hydrocarbons by providing an insulating layer between the concrete and the cryogenic liquid. And it should be noted that this is a passive system, that it remains in place until it's needed and does not require deployment to become effective. This is a concept that foam glass has done many years research before we developed this exact system. Back in 2014, we conducted testing where we constructed square pits using 38 millimeters of our foam glass 1 insulation. We then applied those square pits over a steel plate as well as a 25 millimeter concrete paver. Liquid nitrogen was added to each pit at -196 degrees Celsius. We then attached thermocouples between the foam glass insulation and the structural material and measured the interface temperature for 60+ minutes. Here you can see the results of that interface temperature between the foam glass and the steel plate. On the bottom, you can see the temperature range where you start to get worried about potential carbon steel embrittlement. And you can notice that over the course of a 60-minute test, we were able to maintain an interface temperature well above where you start to get concerned over that temperature range, never dropping below around 8 degrees Celsius. And it's a similar story on the end of the concrete and foam glass interface temperature. Again, you can see the temperature range down below where you start to worry about potential microfractures to occur and a reduction in load-bearing capacity. Over the course of 90 minutes in this case, we were able to maintain an interface temperature safely above this temperature zone where you have to worry about instances like that. So what exactly is this system? What does it consist of? What are the components used within it? Well, there actually are a few different configurations you can use to achieve a system like this. The one we're showing you here today involves using our foam glass 1 insulation with our PC 700K coating pre-applied. Now this 700K coating is a pre-fab shop applied coating that adds thermal shock resistance to our foam glass insulation. So the foam glass will show up to the job site with it pre-applied and ready to be installed. Then would pair this foam glass with one of our PC adhesives as well as our PC 80M mortar for use on those 700K joints. You would then pair it with a protective coating and a UV coating to go over top the system and add it for weather resistance. And then we also recommend the use of our PCF anchors to help maintain the system stay in place throughout the life of the facility. Here you can see a visualization as to what this system may look like when it's installed within an actual pit. Note that this system can be applied in either single or double layer configurations. I have here shown a double layer. In this instance, you would start by applying your first layer by putting PC adhesive on the inside face of the first layer of foam glass, and then using F-anchors to help fasten them to the actual concrete wall of the pit. You would then apply the second layer, again using a PC adhesive over top the first one, making sure that the PC 700K coating is on the outside facing into the pit itself. You would then apply the various protective coatings that we would recommend to help ensure weather durability throughout the life of the system. And at the end of the day, you'd like to flash the top of the wall at the top of the pit with metal to help prevent water ingress from getting in behind. So we just covered our Cryospill system and its various uses within containment pits. Now we're going to move on to our second system that we're going to discuss here today, which is our foam glass LNG pool fire suppression system. So what is our foam glass pool fire suppression, or PFS Gen 2 system? Similar to our Cryospill system, it is a system that leverages the unique properties of our foam glass insulation. It is a low maintenance solution that delivers reliable and passive protection and is meant to complement any safety programs that your facility may already have in place. It provides reduction of vaporization of liquid hydrocarbons by providing an insulating layer that floats atop the cryogenic liquid surface, and it reduces the rate of combustion and flame height of any flames that are present within the pit. So what exactly does this system consist of? Well, it's essentially modules of our foam glass 1 insulation, as we've identified earlier, wrapped in a silicone adhesive coating and then cladded in stainless steel. These modules are then connected together using stainless steel bridges and screws. And for those curious, this is a patented system of ours. Our specific patent number can be seen there below for further reading if interested. How it works. So like I mentioned, this is a passive system. It actually remains in place within the containment pit or trench until it's needed, and it assists in providing immediate and automatic control of LNG pool fires without any deployment delays. The way it works is because the foam glass 1 makes up a bulk of the material, the modules are actually highly buoyant in the presence of LNG due to the fact that it's a closed cell insulation. So in the event of a spill, the modules quickly rise to the surface of the LNG and provide an insulating cap that can aid in the reduction of vaporization atop the surface. Now, worst case scenario, in the event of ignition, the modules will quickly mitigate the burn rate of any fires that are present and limit the thermal radiation and flame height that exists. Basically, it takes up so much surface area atop the LNG surface that it doesn't allow too much fire to really exist even if it wanted to. And on the bottom, as you can see there, this system is meant to work in conjunction with any firefighting foams and chemical extinguishing systems that you may already have in place. So here's a quick overview of various systems and components that come with the system. On the left, you can see the modules that we've been discussing already. We do send it over with pre-drilled screw holes within our bridges that you can use to fasten them together. We also include extender plates that you can use at the end of rows of modules to help accommodate for any gaps that may arise because of unique pit geometries that we have to work around. We also include the exact screws that you'll need to install the system, as well as there's the potential to include optional screw legs for supports of the individual modules. Now, talking a little bit more about these screw legs, why would you want to pursue supports for these individual modules? Well, it basically comes down to the environment and location of your exact pit in question. If your pit is exposed to significant precipitation, we actually recommend the use of supports such as this because it helps channel water out from underneath the system and aid in allowing the system to quickly rise in the event of a spill. Options for these supports include the support legs, as you can see here. We also cover a fiberglass reinforced plastic grating within our guide specification, but we're also open to any customer-driven solution that may also work. So if you have an idea for some supports that would work for your facility, feel free to let us know. We'd be happy to have a discussion around just that. Now, with every project that we pursue this PFS system with, we always like to start with a custom layout built from scratch for your specific pit geometry. No two pits have the same exact dimensions, and we really like to make sure that your exact pit is getting the right configuration for your needs. Now, we have a certain methodology that we approach when we're constructing these custom layouts. But in general, we want to make sure that all modules are bridged together with our custom bridges and screws to minimize gaps wherever possible, both between modules themselves as well as between the modules and the adjacent pit walls. And any obstructions should be designed and worked around. This could include changes in elevation within the pit, any pipes, ladders, or equipment that exist within the pit, and any gaps that exist because of these obstructions should be flashed with metal whenever possible. One final thing I'd like to point out is that this system will perform the best if the LNG is allowed to enter the pit from underneath the modules. So if you're a facility owner that has flexibility in how you can have your LNG enter your pit, we always recommend to have the LNG approach from the bottom of the pit as opposed to from the top overhead. Here you can see some photos of the installation of this system being done in the real world. We ship all the components of this system out at the same time. So once all the components arrive on site, it's a pretty basic set of steps to achieve to getting the system installed properly. In essence, you want to unpack the modules and their components, lay them according to our diagram, and then fasten them together with our screws that we provide, making any necessary field adjustments necessary so that at the end of the day, you have a proper fitting system for your pit. Similar to our Cryospill system, this is a system that we've done extensive testing on over the years. We've actually had testing conducted by the Resource Protection International back in Spain in 2013. This evaluated the effectiveness of vapor and heat flux control on LNG and LPG. It was done in a 4 square meter containment pit with 4 radiometers placed 5 meters back from each corner of said pit. And a full report is available on our website for this test report if you are interested. So this test actually began using that pit that we just described with no suppression system installed. 1.5 cubic meters of LNG was released into the pit. The LNG was then ignited and allowed to burn freely. The vapor cloud was observed and the heat flux was measured using the 4 radiometers. Here you can see the results of those 4 radiometers over the duration of this initial test. You can see it fluctuate quite a bit, but in general, we're looking at readings from between around 3 and 8 kilowatts per meter squared from each radiometer around the corners of the pit. The next step for this test was to do the same exact procedure after installing our PFS Gen 2 modules within the same pit. So after lining the pit with our modules, we applied the same 1.5 cubic meters of liquid natural gas, observed the vapor cloud that was formed, ignited the LNG, and allowed it to burn for 30 minutes. Here you can see the results of the second round of testing with our PFS Gen 2 modules installed in the pit. You'll notice that once steady state is achieved, all of the radiometers are showing readings safely below 1 kilowatt per meter squared. Now I would like to call attention to this initial spike that you see here on the left side of the graph. This is an expected phenomenon to see at the beginning of a test like this. The LNG was introduced to the pit several minutes before it was ignited. This spike in heat flux is a combination of the burning of previously vaporized LNG as well as the vaporization and burning of residual LNG resting on the modules and sidewalls of the containment pit. Once these initial vapors were allowed to burn off, the measured heat flux reached a steady state, evidence of the reduced vaporization and burn rate that's taking place. And here you can see the average of all 4 radiometers plotted under steady state conditions for both the original reference test as well as the second PFS Gen 2 round of testing. And here you can really notice, when plotted on the same graph, just how drastic the reduction in radiant heat between the first and second round of testing was with our PFS Gen 2 system. One additional benefit that we like to mention around this PFS Gen 2 system is the fact that upon conclusion of the second round of testing, someone was able to approach the pit wearing proper PPE and actually extinguish the flames using nothing but dry chemicals. This is not something that would traditionally be possible in the same containment pit when no suppression system is installed. So we've now introduced both our PFS and our Cryospill systems independently. Let's take a little bit to discuss how they can benefit off of each other when used in conjunction with one another. One of the capabilities of our technical services team here at Foam Glass is the ability to run various energy analysis calculations for your specific pit and/or application. Here we have a hypothetical instance of an LNG containment pit that we're going to run an energy analysis report for. This LNG containment pit is about 4.5 meters wide by 4.5 meters long by about 3 meters deep. It has 15 centimeter concrete walls with a ground temperature of around 20 degrees Celsius, an air temp of 24 degrees Celsius, an LNG temp of negative 160 C, and you can see there the LNG heat of vaporization at 512 kilojoules per kilograms. Now, with no insulation used, no protection system installed, the total heat gain into the system is about 32.5 kilowatts, equating to a boil-off of around 3.8 kilograms per minute of LNG. Just by installing our PFS system, that total heat gain can be reduced to 9 kilowatts, equating to a boil-off of just over 1 kilograms per minute. And by utilizing both our PFS system and 50 millimeters of our Cryospill system, the heat gain can be further reduced to just over 4 kilowatts, equating to a boil-off of under half a kilogram per minute. And this all equates to an 88% reduction of LNG boil-off by incorporating the use of both our PFS and our Cryospill insulation systems. Here in front of you, you can see the same exact calculation performed using imperial units, just for anyone in the audience who would be interested. Here you can see a visualization of what a containment pit may look like in the event of a spill with no insulation systems in place. As you can see, the LNG is in direct contact with the concrete of the pit itself, as well as the warm air above and solar load that may be overhead. And you can see a very rapidly developing cloud of vapor that is apparent over the surface of the LNG. Once again, this visible cloud is not directly the problem. It is condensed water from the air. However, it is strongly indicative of the presence of flammable fumes being given off from the pool. Now, by incorporating the use of our PFS Gen 2 system, a lot of this vaporization can be reduced just by providing that insulating cap over the top of the liquid natural gas. That's going to prevent a lot of the heat from the warm air and sun above from entering in, and it's also going to provide an insulating cap that can reduce the flame height and radiant heat given off from any fires that take place. And then obviously, you can go a step further and incorporate the use of our Cryospill system as well, that further reduces the rate of vaporization by adding an insulating layer between the concrete and the LNG, as well as protecting the concrete and steel rebar within your containment pit from cryogenic thermal shock. So now we've just introduced both systems that I wanted to talk with you about here today. I'd like to just take a few minutes to discuss some technical resources that we as a foam glass business can offer you and your installation needs. Starting off, we do offer a multitude of guide specifications, not only for these two systems we've discussed here today, but for a wide variety of systems that incorporate foam glass in various applications. These guide specifications give you examples of how language may appear within use of your own specifications, as well as best practices for use when actually applying these systems in the field. We've actually already discussed that we can perform energy analysis reports for your various needs. Should you be interested in thickness recommendations, finding out the boil-off rate for your specific containment pit? Would you be interested in heat flow for another application you have, or just process control in general? Feel free to reach out to us. We'd be happy to get you an energy analysis calculation for what your specific needs may be. Our team also offers site energy surveys to be performed at your specific site location. We have multiple certified thermographers on our staff, myself actually included. We can show up, take thermal images of your various processes, your equipment, show you where you may have heat bridges, excessive heat gain or loss in or out of your system, show you how your current insulation is performing, and give you a general idea as to whether or not you should be considering maintenance on your current insulation systems. We frequently offer a variety of application training courses at one of our global training centers around the world. This may consist of a 1 to 2 day in-person training course where installers, specifiers, or anyone who's interested can show up, get their hands on our foam glass insulation, and really learn some best practices around installing these systems in the field themselves. Pictured here, you can see an image of the inside of our training facility in Fresno, Texas, here in the United States, but we also have similar setups in Tessenderlo, Belgium, as well as in Yantai, China. And finally, we do offer project site support for any specific projects that you may have upcoming that you feel need it. If you have a specific project in mind and you'd like to have one of our qualified staff members on site, training your installers, making sure that your site gets started up the proper way, we'd love to do our part to discuss with you on how we can make sure that at the end of the day, you have a properly working insulation system on your project. With that, I'd like to thank you all here again. If you have any questions, not only on the topics we discussed here today, but anything else insulation related, you can feel free to reach out to our technical services and training team. Our phone number and email address can be seen listed there, as well as our website. My name and email address is also listed there. I'd be more than happy to address any one-on-one questions that you may have. With that, I'd like to thank you all again for your attendance here today, and please enjoy the rest of your day. Thank you.